Dream to become the next Sir Isaac Newton or Albert Einstein? Learn from the master, Refat Bari. Watch his videos to achieve your dream.
Now, hopefully everyone here remembers what the dot product is. The dot product is, you could say, one of the most important operations in applied mathematics. It is important in everywhere from finance to applied mathematics to science to electrical engineering to mechanical engineering, everywhere. It is omnipotent. And today we're going to be looking at one of the most amazing properties of orthonormal matrices, or some special matrices in general, which is that they preserve the dot product. Okay, so first and foremost, today's do now is going to begin with the definition of the dot product. I think that's a good place to start. Boom, we've got some really excited students, as you can see. They all love the dot product. We're all fans of the dot product here at Very Science. Without the dot product, we could not function. And neither possibly could you. So let's go ahead and turn that down. There we go. A nice clean slate is something we always like to have. So preservation of the dot product. Okay, we're going to begin with a simple do now, and that do now is going to ask you for the definition of the dot product. Okay, so there's actually 3 different definitions I like to think of when discussing the dot product, and here they are: A dot B, A dot B, and of course A dot B. Wow. Thank you. I appreciate the gratitude. Now, go ahead and evaluate, or at least give me some colloquial definitions of the 3 ways of defining the dot product. I'll give you a few seconds, and good luck. Okay, hopefully that was enough time to do the do now. For our first definition of the dot product, we're going to go nice and simple, which is quite simply the magnitude of A times the magnitude of B times cosine of the angle between them. Okay. Then for our second definition, we're going to take a look at the sigma definition of the dot product, which is quite simply sigma of I to n. I'll be simplifying my notation a little bit, but if you really don't understand, go ahead and take a look at our first couple of lectures. So sigma of I to n of what? Of what? Even I don't know at this point, but actually I do. It's A sub I times B sub I, and that's it. It's the second definition of the dot product. And our final definition of the dot product is a kind of informal visual one, right? To kind of assist you with the idea that the dot product is indeed a projection of one vector onto another. So, say I have 2 vectors generally in the same direction, don't have to be, but for the sake of my argument. And I'm going to project my vector v down to u, and I'm going to get something like this, something like that. So my projection of v onto u multiplied by the magnitude of u is going to be equal to the dot product between these 2 vectors. Okay, so these are the 3 most famous definitions of the dot product. Hopefully you're accustomed to them by now. So we're going to transition into our lesson. Let's grab a marker and transition into our lesson. Now, the amazing thing is that the dot product is not preserved between linear transformations. Because linear transformations, they tend to usually, not always, but non-rigid linear transformations tend to stretch or dilate or compress vectors, to squeeze them. As a result, the dot product often increases or decreases depending on the nature of the transformation. So you cannot always expect the dot product to be preserved. But in the case of orthonormal matrices, I sense something special. Maybe the dot product could be preserved, but how can we test that? Well, let's take a look at one orthonormal matrix, shall we? So let's go ahead and write it down. So here we are. Now, a useful skill, if you forget the square matrix of order 2 that holds the rotational matrix, is as follows. You can derive it as such. You don't have to do that 30-minute, half-an-hour derivation. You can just take a look at the unit basis vectors and how they change. So, let's go ahead and take a look. Right? So, these are my unit basis vectors. And what I'm going to have is, let's say, this vector right here. That's going to be my I hat. It's going to be my I hat. This vector right here. That's going to be my j hat. I hat, of course, being 1 naught. J hat, of course, being 0 naught. And I want to find, of course, if I know that if I rotate them 90 degrees, what's going to happen is if I rotate them 90 degrees clockwise, at least, I'm going to get something like this. I hat becomes 0, 1, and j hat becomes negative 1, 0. Okay, so what can I do to achieve this? Well, let's take a look. To even rotate this vector 1, 0, 0, 1, what am I looking for? Well, I know I'm going to have sines and cosines in there, right? I'm going to have what? Cosine theta, right? And sine theta minus cosine theta, sine theta. Let's say that's my matrix for a moment. Let's go ahead and test that out, right? So if I go ahead with a 90-degree transformation and I plug in 90, 90, 90, 90, what am I going to get? Well, that's simply going to end up being, well, what's cosine of 90? That's 0. Negative cosine of 90 is still 0. Sine of 91, sine of 91. So that's going to give me 0, 1, 0, 1. And what am I going to get for that? Well, that tells me my I hat is going to go from where to where? Well, if I go ahead and multiply this with my original I hat, which is 1, 0, that tells me to take one of the first column, which is 0, 1. Okay, that means my I hat is going to go where j hat was, which seems like I'm dealing with the right vector, right? So everything looks good, everything looks fine and dandy. We're ready to steam forward. Okay, so how can I check the preservation of the dot product under some matrix? Well, here's the idea I'm thinking of. Okay, so that is, of course, our rotation of the matrix. Now let's say I have my good old two-dimensional Cartesian coordinate plane. I have two vectors u and v. Actually, let's call it u and w, just so that I don't get mixed up. And let's say there's an angle theta separating them. Okay. And of course, u is going to have some two-dimensional components, much like w. Now, the key question is, if I take the dot product, what am I going to get? Just in 2 dimensions. What will their dot product be? Well, the dot product is simply going to be, let's say u has, let's give them some coordinates, a, b, and let's say w has coordinates, components of c, b. Okay? So, what's going to happen is, well, I actually want to make this nicer, so let's go ahead and draw this one nicely. So here we are, no need for a lesson right here, we all know what's happening, so here's my two vectors u and w. My components for u are going to be a, b. My components for w are going to be c, d. And my goal is to check out whether the dot product is going to be preserved under this rotational transformation. Okay, let's take the dot product in R2 before we transform anything. Okay, so what's that going to be? First and foremost, that's R2. So that's going to be what? U dot W. Hopefully you remember from the do now. The dot product is going to be what? Well, the dot product is simply going to be the magnitude of U times the magnitude of W times cosine of the angle between them, which in this case happens to be theta, a general angle. Now let's do the same thing after we transform them. So let's transform U and let's transform W. Let's take their dot product and let's see what we get. So here is cosine theta, sine theta, negative cosine theta, sine theta of U, and U is going to have components A, B, so I don't know, I might as well write those down. A, B, and that gives me what for the components of U after I transform it. I'm going to get A cosine theta minus B cosine theta, and then I'll have, right, and then I'll have A sine theta minus, or sorry, rather plus B sine theta. Okay, hopefully that makes sense. Hopefully that's handy and handy. And now, if you notice, of course, any mistakes in my rotational matrix, please go ahead and write that down in the comments below. Now what I'm doing is just going ahead and giving you a few seconds to go ahead and check out whether you understand what I've just said, whether this makes sense. Go ahead, take a few seconds and digest that. Okay, so hopefully that was enough time. Now what we're going to do is replicate what we just did, but now instead of U, we're going to do that for W. So W, of course, happens to have components CD, and of course, what is CD going to be after I transform it? Well, I'm going to give you a few seconds to go ahead and check that out. Okay, so hopefully that was enough time. Now, in the interest of not having my head cut out, what I'm going to do is check for a moment that I do indeed have the right rotational matrix, because I do feel a bit insecure about this one. So let me just grab a new marker here. So brand new marker right there, and totally fresh out of the box. Now let's take a look at what we're dealing with here. If I have some vector, let's say this is right here, say this is 1, root 3 and 2, so this is 30 degrees rotated, right? Sorry, 60 degrees rather. So I'm rotating this vector by 60 degrees, so let's see what its components before and after are. Well, let's just do 30, right? So I'm going to have what? 1, root 3, and 2. So before, its coordinates were what? My x component was root 3 naught, and my y component was 0. Then after rotating it, my x component was still root 3, but now my y component was 1, right? So now, let's see if this matrix actually does what I expect it to do. Right, after I plug this in for theta of 30 degrees, will I get root 3 comma 1? Well, let's go ahead and check it out. Plugging in 30 here is going to give me what? Cosine of 30, of course, being the same as sine of 60, which is what? Root 3 over 2, folks. Root 3 over 2. So I'm going to have what? Let's write this matrix down. Root 3 over 2. Sine of 30, don't forget, it's going to be a half. Negative cosine of 30, negative root 3 over 2. And of course, sine of 30, once again, half, right? Now, we're not done. We're just getting started, as a matter of fact. If I go ahead and multiply this by root 3 over root 3 is 0, that tells me to take root 3 of only the first column. So then I'll be left with what? I'll be left with 3 over 2, right? And root 3 over 2. That's clearly not what I have right there. So something is already with my rotational matrix, and that's what we're going to discuss in today's exit slit. Okay, unfortunately we didn't get to actually showing the preservation of the dot product under orthonormal matrices, but we will be discussing that in our next lecture. So let's take a look at the exit slit, which of course is extremely long for this one.
Excuse me, your lectures are that might be interrupted.
Sorry,
Shorten them?
yes, I'll make them longer if you
No, I
say
said shorten.
Yeah.
Yeah.
Shorter and
Even
longer.
Mr. Rodriguez wants this.
I could do this all day and night.
We want change.
Alright, so today's exercise we're going to take a look at how we can kind of, oh yes, I do have a head. Let's take a look at what our exit flip is. Our exit flip today is going to be focusing on actually verifying the transformation matrix and how to derive it on the go without doing the half an hour proof or the derivation that I did over the last 3 lectures. Okay, so that is our exit flip. Go ahead, take a few seconds to grasp that, and then I'll give you the full solution. So good luck, and I'll give you a few hours to go ahead and try the exit flip.
A few hours.
Okay, a few seconds.
You're
A few
going to
seconds.
leave us hanging here for a few hours? The bell will be ringing by then.
Alright, hopefully that was enough time. How do we actually derive a transformational matrix for 2-dimensional rigid transforms on the go without wasting half an hour? Let me show you that right here, right now. Now, let's say I have some arbitrary 2-dimensional vector in R2, and of course for the crazy ones out there, I'll just write that it's an element of R2, so you know what we're working with. And let's say I start out with some vector, let's call it U. Okay, and I'm gonna give my vector some components. Let's say my vector has components of 1 naught. So this is actually I hat, if you recognize it as such, but we'll let it go. Now, let's say I rotate this vector U, or I hat, if you want to be picky, by 30 degrees. 30 degrees, is that right? 30 degrees. Okay, what am I gonna get? Well, I know that this is gonna be 1 simply by the ratios of a 30, 60, 90 triangle, and this y component is gonna be root 3, and my hypotenuse is gonna be 2, right? So this is a nice lecture. Now, so what will my rotated vector be? My rotated vector will simply be as follows. It's going to have an x component of 1 and a y component of root 3. So what I want my transformation matrix to do is take some matrix A, plug in my original vector 1, 0, or as I like to refer to it, I hat, and suck in or suck out 1 root 3. Okay, and I'm looking for the A that does exactly that. Now, how can I do
Also,
that?
you
Well,
have no audience anymore.
that's fine. I'm fine without an audience, and you should be too. Now let's take a look. What my input vector does, it's saying take one column, take the first column of your transformation matrix A. So it's really not going to be telling me anything. It's not going to give me any information whatsoever about my second column. So really all I have to focus on is my first column, right? Now think, the sine or cosine of what angle is square root of 3? Right? Think about that. So let's go ahead and write that down. So we're rotating by 60 degrees. So I can just go ahead and write that down. Sine, oops. Do we have our eraser? So let's go ahead and write it down. Cosine of 30, sine of 30, right? So does that work? No, because sine of 30 is of course going to give me a half. So I have to switch up my strategy a little bit. Let's say that this is sine of 60 instead, and this is cosine of 60. And once again, you should notice that I'm not going to get 1 as my x component if I do that. So I once again have to change my strategy. What is going on in this vector? Well, I start with 1, 0, right? That's my x and y component. And then I rotate this vector by 60 degrees, right? So you can imagine we have a 30, 60, 90 degree triangle right here. And so I have 1 root 3, 2. And so that's going to have an x component of 1 and root 3. So, in other words, I'm basically asking what matrix is going to have a first column that has these components. 1 and square root of 3. So, what is the sine of 60? Sine of 60 is, of course, root 3 over 2. It's not root 3. So are we making a mistake here? Well, let's see. 1 plus 3 is going to give me square root of 4, which is 2. So I'm going to be asking the viewers what is wrong with this transformation matrix. Go ahead, try to solve it, and we're going to figure it out in the next lecture number 79. Good luck, and we'll see you.
Subscribe to Bari Science Lab to fall in love with math and science, especially programming.